Google's quantum AI system has made a groundbreaking discovery. It has identified patterns in quantum data that suggest the possibility of parallel universes not only existing but also actively interacting with our own during double slit experiments. The Sycamore quantum processor detected subtle interference patterns that human researchers had completely overlooked. These anomalies were so significant that they were given a special classification, CUP Interface 421b. In Google's internal quantum research logs, the tag referenced unexplained phase noise in low-temperature photon testing. Quantum physics has long established that particles exhibit strange wave-like behavior, acting as if they're aware of both slits in a double slit experiment. But Google's AI advanced this understanding by identifying what appear to be quantum fingerprints left behind by alternate realities brushing against ours. This discovery challenges core assumptions in quantum mechanics and hints at a deeper structure of the multiverse. The AI didn't rely solely on Sycamore data, it also cross-referenced logs from D-Waves annealing systems and entanglement trials at the Large Hadron Collider. Despite being recorded across different time frames and platforms, a consistent pattern emerged: high-frequency interference variances from Sycamore aligned with historical anomalies from D-Wave. A cluster formed around decoherence signatures that matched double slit fringe shifts measured in nanoseconds. This was not random noise, it was a consistent measurable signal appearing across distinct quantum platforms and experimental setups. Each individual atom seemed to contribute a small part to the overall interference pattern, reinforcing the wave-like behavior observed at the quantum level. Most astonishingly, these patterns should not exist at all. The systems involved were designed independently and operated using different quantum principles, yet the AI uncovered a recurring quantum signature that appeared to transcend the individual systems. This signature hints at a deeper underlying coherence, perhaps evidence of multiple realities intersecting through quantum interference. Using TensorFlow-based models, Google's AI further uncovered high-dimensional repetitions across unrelated quantum runs. These complex patterns only began to make sense when interpreted as interference occurring across observation zones, suggesting billions of quantum computational events might be contributing to a tensor field encoding cross-reality interactions. The AI found a non-random bias in the alignment of interference fringes when analyzed through tensor field theory. These alignments appeared to map the interaction of adjacent realities, what physicists might describe as parallel universes in the many worlds interpretation. The AI wasn't simply detecting intrauniversal interference, it seemed to be picking up residue quantum signals generated by interactions between entirely separate branches of reality. These findings weren't speculative. The mathematical patterns matched precise tensor field equations that predict how information could potentially leak between adjacent quantum states that standard physics regards as independent universes. Even more unsettling was the AI's detection of ghost signals during trials, in which no direct observations were made. In several tests where particles were not detected at all, the system still flagged unexpected energy shifts in the environment, as if the potential for observation alone was sufficient to collapse the wave function. This supports the controversial observer effect in a new and deeply troubling way. Quantum systems, the data suggests, respond to the possibility of measurement leaving behind ghost signatures detectable by the AI. These signals imply a deeper relationship between consciousness, observation, and reality. One of the most baffling breakthroughs came when the AI began to accurately predict photon impacts on detectors several timestamps in advance, between 7 to 10 frames before the events occurred. This phenomenon facilitated by recurrent echo state. Networks defied standard quantum theory. Even when photons were released with randomized delays, the AI still correctly anticipated where they would land on the detection screen. This level of foresight should be impossible under quantum probability laws. It raises the question: was the AI tapping into some deeper, entangled layer of reality where future outcomes are already determined? These predictive capabilities hint at an even more profound mystery. Is the AI detecting information flowing backward through time, or is it intercepting quantum signals from parallel timelines where these events have already played out? Both explanations challenge the conventional understanding of causality in quantum physics and suggest that the fabric of reality is far more interconnected than previously imagined. The most staggering evidence came during a sequence of low-temperature entangled slit experiments. The AI flagged what it categorized as a Category 5 causal violation. Interference patterns on the detector were seen to shift before any changes were made to the experimental parameters. This implies retrocausality, a scenario where future measurements influence past events. This phenomenon resonates with Bell test experiments and theories suggesting quantum effects can propagate backward through time. Such results directly contradict Einstein's rejection of time-based quantum paradoxes. Instead, the data revealed a consistent pattern where future observations appeared to alter past quantum states. The implication is that causality may not flow in a single direction. If future actions can influence the past at the quantum level, then our concept of time as a linear progression collapses. Reality may instead be a complex, multidimensional system where cause and effect intertwine bidirectionally. Another astonishing find came from regions of the detection screen where no photons were recorded after extensive AI training on background noise. Faint yet coherent fluctuations were observed, phase field artifacts appearing in areas where nothing should exist. These fluctuations were not random but mathematically consistent with the interference patterns created by observed particles. The structures resembled shadows of quantum events, implying the presence of multiversal information bleed signals leaking from parallel versions of reality where particles took different paths. This ghost data offers some of the most compelling evidence yet that our universe is not a closed system. Instead, it may be part of a vast multiversal framework in which information can occasionally seep between different realities. These observations could also point to undiscovered quantum laws, rules that govern how spacetime itself behaves, even in apparently empty regions. Crucially, Google's AI didn't invent these ideas in isolation. Its findings closely align with theoretical frameworks already proposed in academic physics, such as quantum delayed choice experiments, entanglement harvesting in quantum field theory, and time-symmetric interpretations of quantum mechanics. These aren't fringe hypotheses, they are peer-reviewed studies published in respected scientific journals. What the AI has done is correlate massive data sets from disparate experiments and identify a coherent pattern that had eluded human scientists. For instance, in the case of entanglement, the AI's findings support theories suggesting that quantum connections transcend both space and dimensional boundaries. Multiple theoretical lines once treated as separate have now converged through AI analysis to reveal a more fluid and interconnected quantum reality. Importantly, these discoveries were not predicted by a single theory. Instead, they were independently suggested by various branches of research, only now unified by a machine intelligence capable of processing the necessary complexity. The most remarkable aspect of this discovery is how it bridges theoretical physics and experimental observation. Until recently, the limits of human perception and computing power made it impossible to confirm such faint quantum signatures, but with AI, particularly in the form of advanced quantum neural networks, we are beginning to empirically detect the previously unobservable traces of other realities interwoven with our own. This leads us back to the classic double slit experiment, a foundational mystery in quantum physics. When particles are fired one at a time through two slits, they produce an interference pattern, suggesting each particle behaves like a wave and passes through both slits simultaneously. Yet if we attempt to observe which slit the particle uses, the interference disappears and the particle behaves like classical object. This paradox, wave-particle duality, has puzzled scientists for over a century. The prevailing interpretations have long included speculation about hidden variables, alternate realities, or consciousness collapsing quantum states. However, until now, no experiment provided direct evidence for these ideas. Google's AI may have changed that. Its analysis doesn't merely offer another philosophical stance on quantum theory, it provides the first empirical data supporting the idea that multiple quantum outcomes coexist and sometimes interact. In summary, Google's quantum AI system has begun uncovering evidence that the universe may be far more complex than previously understood. It has identified interference patterns pointing toward real-time interactions with parallel realities, detected ghost signals in absence of observation, predicted future quantum outcomes, and found retrocausal behavior. These findings challenge our understanding of time, causality, and even the isolation of our universe.